In this lesson, we are going to solve rational equations and rational inequalities. So far, we've talked about rational functions, and the big focus was on graphing rational functions. And in fact, I would argue every time we teach you a new function, the very first thing we do is teach you how the function looks like graphically. Okay, we always provide you the graphical approach first, and then we throw the algebra at you. So for example, with polynomials, what did you do first? You graph the polynomial function, and then you learn how to solve polynomial equations and polynomial inequalities. Same thing here. We teach you how the graph of rational functions look like, and then we're going to toss these rational equations and rational inequalities at you. Okay, so what we're going to do is solve rational equations first, and then solve rational inequalities. So the approach to solving rational equations is pretty straightforward, to be honest with you. In fact, I would argue it's a pretty good idea to teach these in grade 9, because whenever you solve a linear equation with fractions, what did you do in grade 9? Okay, so you know what, let me just write this. Grade 9 equation you got. I don't know if you actually saw these in grade 9. You should have. So this is something you may have seen in grade 9. So what would you do? You would multiply both sides by the lowest common denominator, because it's not that you have to multiply both sides by the lowest common denominator or the least common multiple. It makes sense to do so because you clear the denominators. The 5 and the 2 and the 7 will quite simply become 1, so you don't need to write the denominator. Okay, and by clearing the denominator, the algebra becomes much more straightforward. So we're going to have the same approach here. What we're going to do is multiply both sides by the lowest common denominator, and then you will clear the denominators, and you convert this rational equation into an old friend of ours. I don't really want to spoil it, but it's our old friend. Okay, so you know what? What's the lowest common denominator? X times 3x minus 5. So 4 over 3x minus 5 times x times 3x minus 5. 4 times x times 3x minus 5 plus 2 over x times 3x minus 5. Okay, beautiful. So we multiply the left side and right side by the lowest common denominator, and guess what? Common factor. So you're left with 4x equals 4x times 3x minus 5 plus 2 times 3x minus 5. So what do you see here? You go from a rational equation to our old friend polynomial equation. Isn't that nice? Okay, so we know how to do polynomial equations. Expand, set equal to 0, and just factor. Set equal to 0, so the negative 20 plus 6 is negative 14. Negative 14 subtract by 4 is negative 18x. Let me triple check that. Negative 14, yep. And divide everything by 2. And unfortunately, this is actually not factorable. So guess what? We need our old friend from grade 10, our quadratic formula. So let's see, 81 plus, it's 201 over 12. All right, now there is one difference between rational equations and polynomial equations, and that difference is with restrictions. Okay, you have to state the restrictions equation, because sometimes the solution you solve for matches up with the restriction to the equation, you have to end up rejecting that solution or that root that you solved for. So you know what, let's take a look at this equation and determine what the restrictions are. This is very similar to what you did in grade 11 when you worked with rational expressions. What are the restrictions to that expression? And in this case, what are the restrictions to that equation? So look at this, 4 over 3x minus 5. So the restriction x for that is 5/3, okay? If we solve for x and it said x equals 5/3, we have to reject that. Because if I check left side equals right side, left side would be undefined if x were to be 5/3. So if I solve for a root and it matches with one of my restrictions, I cannot accept it. I have to reject that root. It's called an extraneous root, okay? There's actually one more restriction in this equation, that's 0. X cannot be 0. So that's just one little difference between solving rational equations and polynomial equations. With polynomial equations, you'll have no restrictions, okay? Because you can never make the left side or the right side undefined. But with rational equations, there's a possibility of having values of x which make left or right side undefined, and you have to identify those values in the form of a restriction. So after you solve the equation, just quickly check if they match up with your restrictions. If they do, please reject that root. Okay, let's do B. So x minus 5, x minus 2, this is x plus 6, and x minus 2. Ooh, beautiful. Because x plus 6 is a common factor. And then you can multiply both sides by x minus 2, which means you're left with x minus 5 equals 1. So x equals 6. Is this a correct solution? Well, I don't really know. We have to check if it matches up with one of our restrictions. So what are the restrictions? X cannot be 2, nor can it be negative 6. So 6 is a beautiful solution to this equation. How can I double check? I can take it and sub it to our original equation, and you'll see left side equals right side, just like you would check any other equation. All right, good stuff. Let's keep going. All right, x minus 1 to multiply both sides by 2x. Great, so that converts my rational equation to a polynomial equation, right? That first step is beautiful. Okay, let's state the restrictions. And another old friend. Oh my goodness. Well, I know you probably didn't want to see this, but let me just make sure. Minus 4x minus. But our cubic equation. Well, I hope you didn't miss the boat, but this one you can factor by grouping. Old friend here. So x equals negative 3 or x equals plus minus 2. Those are the three roots to this rational equation. Everything is acceptable. None of them are 0. So yeah, I checked them with the restriction. We're all good. Ooh, what about this one? Let's factor to establish what the lowest common denominator is. I can't tell you what the lowest common denominator is. If this is not factored, I have no idea what the lowest common denominator is. That is very similar to what you did in grade 11 when you're simplifying rational functions. Oh, sorry, rational expressions. You never did rational functions last year. Okay. So, restrictions, let's get that out of the way. X cannot equal to negative 3, x cannot equal to 2. Alright, so multiply both sides by the lowest common denominator, which is x plus 3 times x minus 2. Which means this is equal to 1 This will cancel out the common factor of x plus 3, so you're left with x minus 2 all squared. This will be x plus 3 all squared. And 0 times anything is 0. Okay, so after I multiply both sides by lowest common denominator, this is what I have. So first step, beautiful. Rational equation, polynomial equation. Life is good. Okay, expand. Perfect square trinomial. Perfect square trinomial. I'm going to try to skip a step here. Negative 10x. This is going to be negative 9, 5. 5 minus 9 is negative 4. Switch other side is positive 4. Please don't do what I did. Just take your time and show as many steps as you can, as you need. We're running a big risk here. Divide both sides. Negative 2/5. When in doubt, sub it in. Check if left side equals right side. Okay, so on the next page, we're going to do the second half of this lesson, which is solving rational inequalities. So now we're going to solve some rational inequalities. So when we solve polynomial inequalities, we had lots of different strategies. We could solve it graphically, we can solve it using a number line, which was another form of the interval table. We can solve it using cases. So there were a lot of options. So those options are still available when you solve rational inequalities. But in this lesson, we are going to focus on solving them algebraically. Can you solve it graphically? Of course, okay? But be careful. Solving it graphically may take longer because graphing a rational function is more time consuming than graphing a polynomial function, even with all the shortcuts I've provided. Okay, so sorry, I forgot to mention, I gave you a beautiful graph here. When solving rational inequalities, it is important to remember that your x-axis is divided into intervals by critical values. So previously, with polynomial inequalities, you imagined a polynomial function, and the x-intercepts divided the graph into the intervals where it's positive and negative. But with a rational function, it's not just x-intercepts. There are holes and there are vertical asymptotes, which divide the function into different intervals. So you have to establish where the x-intercepts are, where the holes are, and where the vertical asymptotes are. So I try to show you a beautiful graph of a rational function where it changes signs at a vertical asymptote, at an x-intercept, and at a hole. To show you why we need to find those values and divide the number line into those respective intervals. Okay, so similar to a polynomial inequality, you have to set one side equal to 0. Okay, so 2x plus 1 all over x plus 4, subtract both sides by 1. I'm just going to change that 1 into x plus 4 over x plus 4. Okay, so now that's really messy. Let me fix that up. Okay, so now that's going to be 2x minus x is x, 1 minus 4 is negative 3. So we are asking, when is x minus 3 over x plus 4 is greater than or equal to 0? So like I said, can you solve this graphically? Absolutely. Would I solve it graphically personally? Absolutely not. So what I'm going to do is build a number line. Okay, I actually have two shortcuts. I'll show you both shortcuts of doing this question. So the key values here, the x-intercept occurs at 3, and the vertical asymptote occurs at negative 4. Okay, so there are two factors here. All right, so when x is a very large negative number, both factors will be negative, and when I see two negative signs, I know that it's going to be a positive value, right? Like if I had this negative or negative, I don't care what it's equal to. Negative with negative is positive, so the first interval, when it's less than negative 4, it's positive. And I know I'm going to switch signs as I pass this vertical asymptote because the behavior will be opposite. And then I'm going to switch signs again because it's x minus 3 to the power of 1. So I really want you to connect what we did graphically with what we're doing algebraically. It switches signs. The behavior is positive infinity on the left side and it's negative infinity on the right side. And it makes sense to switch signs because it's very similar to what we did in the first unit when we said the order of the zero is odd. Exact same idea. Okay, if the order of the zero is even, it makes sense because you're squaring the factor or you're raising it to the power 4 or the power 6. It makes sense that the sign doesn't change when it's even exponent. And it makes perfect sense for the sign to change when the exponent is odd. So you know what, take 10 minutes of your time and really connect the dots. Connect the dots, the graphical representation of this inequality with this number line, and also connect what you did last unit with what you did this unit, okay? So really think about it. Okay, so therefore 2x plus 1 over x plus 4 is greater than or equal to 1 when, all right, so when is it greater than 1? So less than negative 4. Should I include negative 4? Absolutely not. Should I include 3? Yes, indeed. There we go. Solve the inequality. All right, so the way I draw my number line, I just, you're saying not real numbers. The way I draw my number lines is I count the factors. Well, at first I create the intervals using the x-intercepts or the zeros and where it's undefined. And then I basically count the factors and I know whether the first interval is positive or negative. And from there, I know I either switch it to a negative or to this positive and so forth and so on. You either change the sign or you keep the same sign. And you can tell by looking at the factors. So B is much easier than A because I don't have to set equal to 0 and simplify. It's already done for me. Okay, how many factors are there? 3 factors. 1, 2, 3. Which means that's an odd number, right? So that means I'm going to have 3 negative numbers which are manipulated through division and multiplication, which means it's going to be negative, switch sign, switch sign, switch sign. How do I know switch, switch, switch? Because all the factors are raised to an odd power. Therefore, let's see, when is it less than 0? When it's less than negative 4 and between 1 and 4. Beautiful. All right. This one, I gotta do some work. I gotta set equal to 0. No problem. No problem. That's my x squared minus x squared minus x squared minus 2x and minus 4x. I'm going to double check that because if that numerator is incorrect, that'd be disastrous. Minus 2x, 1x squared minus 2x. I would not recommend students to skip steps like I did. Just take your time because it's a very common mistake to simplify incorrectly, and then like I said, it's just disastrous. Factor the numerator. Why do I want to factor the numerator? How else am I going to find the zeros? How else am I going to find the zeros? All right, now, bam, bam, bam. I think I'm ready to do this number line here. Some teachers like an interval table. You know what? Go ahead. But if I can find the answer without the interval table, why not? So 0, negative 4, negative 1. Ooh, this is going to be very squished. Let me move this away. Zeros here, let's see. I didn't need that. That was really over dramatic there. I thought I was graphing a rational function there. Okay, and the 2. Okay, all right. So let's count up the factors here. 1, 2, 3, 4. Now be careful. I see a negative sign sticking out there. That means it's 1, 2, 3, 4 times -1. So 4 negative numbers times -1 means that's positive. Oops. Oh, I'm losing my mind. Negative. And see all these factors? All the exponent. Switch signs, switch signs, switch signs, switch signs. And you know what? If I recall correctly in the textbook, all the factors in the homework questions, they're all raised to the power of 1. So you're just switching signs every single time. Yeah, but don't assume that on the test because we probably won't do that. All right, so let's see. Okay, so when is this less than 0? Less than -4, -1 to 0, greater than 2. Beautiful, beautiful. Okay. All right. So let's see the next one. This one seems straightforward. Common factor. It's already set equal to 0. Factor. Ooh, common factor of x. All right. So, there's actually a hole. If you were to graph this, there would have been a hole at x equals 0. Okay, so remember, this interval, this number line is divided using the zeros and where it's undefined. So there's a hole at 0 and -2. There's an x-intercept, and there's a 1 is where it's undefined as well. Okay. All right. 2 factors. So that means this first interval, when it's less than -2, it's positive. Should I switch signs? Absolutely. Now be careful. As you pass this hole, you are not switching signs. Okay, why are you not switching signs at this hole? Because the only time you switch signs at a hole is when you have a picture like this, when the hole is on the x-axis. How do you know if the hole is on the x-axis? Well, if you had something like this. If you cancel out a common factor and the factor remains in the numerator, okay? That's the only way to get the hole on the x-axis. Okay, if there's a common factor between numerator and denominator and the factor still remains in the numerator. So you can think about that and why that's the case and investigate it and think of different examples, but that's the logic between the only way a hole is going to be on the x-axis. In this case, the hole is not on the x-axis, which means it will not change signs as you pass this hole. So it's going to stay negative. And then as you pass 1, it changes signs. Okay, so when is it greater than or equal to 0? Less than or equal to -2 and greater than 1. Let me double check. Okay, yep, beautiful. So the reason I added this question is because I don't want you to thinking that it changes signs at the hole, okay? In fact, it's very rare for it to change signs as it passes the hole, because the only time it's going to happen is if the hole is on the x-axis. All right, this is the kind of question I like to do. Can you imagine creating the interval table for this? That would be crazy. Okay, so I'm going to do a big number line because it looks like a very chunky. So 1/2 -4. Okay, -4 seems like it's the furthest one. Okay. And then this is 0, 1/2. So 0 is, and then 1/2. And then what else? We have -4/3. Okay. -4/3. And then -1/2. Make it prettier here. Okay, and then we have 4/3. I was just thinking, sorry, I got distracted there. I was thinking this would be good practice for my kids, because they need to work with rational numbers anyways. Okay, so let's double check. 1/2, -4, -4/3, 0, 1/2, sorry, -1/2, 4/3. Okay, all right, hopefully I didn't make a careless mistake. Let's count up the factors. 3 plus 2 plus 2 plus 1 plus 1 plus 1, that's 7 plus 3, that's 10 factors, which means the first interval, you're manipulating 10 negative numbers through multiplication and division. The result, who cares what the result is? I know the result will be positive. Okay, now should I switch signs? And that's, the answer is no. Should I switch signs here? No. Should I switch signs here as I pass 2.5? Yes. Should I switch signs at 0? Yes. Should I switch signs at half? Yes. Should I switch signs at 4/3? And the answer is yes. Right? Just look at the exponents. It's pretty straightforward. Remember, really relate this to your understanding of polynomials. Okay? It's really has to do with the order of zeros. And in fact, when I teach this, I explain to students, you can convert this rational inequality to a polynomial inequality. So I'm gonna, this is an extension. Okay? So this could be really converted to this. 0, -1/2, and 4/3. Okay. Wow. Okay, this is a big jump. How come I am able to convert this? Because when you have an inequality, it's important to differentiate it from an equation. You don't care what it's equal to. Who cares what the left side's equal to? You are asking, when is it less than or equal to 0? Not when is it equal to 0. When is it less than or equal to 0? It's a totally different question. And if that is the question, you, instead of saying multiplying and dividing, how about we just have multiply, 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 right? Because when this is less than 0, this must also be less than 0. So the solution to this inequality will be the same as the solution to this inequality, right? Because when this is negative, I assure you this will be negative. Okay? So you can convert a rational inequality into a polynomial inequality. But remember to state the restrictions. Remember? Because the polynomial inequality can be, the rational inequality can be undefined. Okay? The left side can be undefined. But for polynomial, it won't be. So as long as you state the restrictions, you'll be fine. So this, if you're having a hard time why the sign doesn't switch and why the sign does switch, you know what, think back to what you did with polynomials, right? Why did the sign switch? Why did it not switch? Okay. Anyways, so sometimes I teach students, if they're really having a hard time with rational inequalities, they can convert it to a polynomial inequality. So if that's a strategy you like to use on the test, go right ahead, okay? Just don't forget the restrictions. Anyways, so pretend this wasn't there, okay? That is my solution, okay? This has nothing to do with the solution. This is just a little tangent I wanted to show you. So, therefore, 2x minus 1 cubed, x plus 4 all squared, 3x plus 4 all squared, x, 2x plus 1, 3x minus 4, less than or equal to 0. When, okay, let's stare at the number line. When is less than or equal to 0? Over here, negative 1/2 to 0, or 1/2 to 4/3, including, don't forget, one mark here, include negative 4 and negative 4/3. Students always forget this, so one mark off. Okay. When is it less than or equal to 0? So do not forget negative 4 and negative 4/3 as a part of your solution to your inequality. Alright, last one. Okay, what's the solution to this inequality? When is this sucker less than or equal to 0? So you probably forgot this, Pascal's triangle, 1, 3, 3, 1. So this is actually x plus 1 all cubed. Now this one is a sum of cubes. Okay, hopefully then forget that. So it's x plus 1, x squared minus x plus 1. All right. If you forgot the Pascal's triangle for the numerator, you know what? Just factor theorem. Just factor theorem. So x plus 1 is a common factor, so you're left with x plus 1 all squared. X squared minus x plus 1 is less than 0. Alright, so if you look at the denominator here and find out the discriminant, you realize the discriminant is negative. So you're not going to get any values where it's undefined, except for the negative 1 that we stated earlier, because we cancel out the common factor of negative 1. So hey, well, negative 1 is also what it would have been. It would have been an x-intercept, but because of the restriction, you have a hole on the x-axis. So negative 1, you have a hole on the x-axis. So this is one of the rare situations where the function, where this will not change signs as you pass the hole, because the hole is on the x-axis. And we are bouncing off the x-axis here. If you can imagine this graph, so you're not going to change signs. So this is positive, this is positive. So positive, positive. Okay, this is positive, and this is positive. The numerator is something squared, so of course it's positive. And this you can check. You know what? You can do discriminant. Discriminant is equal to b squared minus 4ac, so negative 1 squared minus 4ac. So it's negative 3. This one, the denominator, I know it looks a little funky, but it's strictly positive. So therefore, when is this inequality less than 0? Never! Trick question. It's never less than 0. It's always greater than 0 actually. It's always greater than 0 except for when x is negative 1, because this will be undefined if it were to be equal to negative 1. Beautiful. Okay, so that sums it up for this video. So we solved some rational equations and we solved some rational inequalities. So this basically deals with all the algebra in the unit.